Hey CW Bio, Mr. Kennedy here, and these are your Chapter 17 lecture notes on the history of life. So today we're going to dive into the theoretical origins of the Earth and look at kind of like how the Earth maybe has changed over the course of, billions of years of its existence under current scientific thought. Mr. Kennedy is probably the only person old enough to have witnessed some of these events firsthand. So let me tell you a story about what science thinks happened with the origins of the Earth for Chapter 17. Here we go. So just to kind of sum up the beginning of the early Earth, scientists believe that the Earth formed as a result of some sort of cataclysmic explosion in space. There's not a whole lot of explanation as to like maybe what triggered this thing that they call the Big Bang. But at the end of the day, this is their theory on how our solar system began. Some sort of cataclysmic explosion occurred in space, literally billions of years ago. And as a result of that explosion and this debris field that was created, big chunks of rock under the influence of gravity from surrounding solar systems and gravity at the center of the remnants from this explosion started to spin, right? And as they started to spin in a kind of like unified direction, the bigger chunks of rock started sweeping up the smaller chunks of rock that were traveling faster than they were. So there were all these collisions, and these small chunks of rock basically hit the big chunks of rock so fast and so hard they literally like melted in to the big chunks of rock, making the big chunks of rock like bigger. At the end of the day, after who knows how long, you are left with a handful of big, giant chunks of molten rock, which we might now refer to as our planets and moons, just orbiting a primitive sun. So scientists think that at this point in our Earth's history, the Earth was probably pretty hot. Probably didn't even have a crust for you to stand on. It was like a giant molten ball of lava, not a breath of oxygen in the atmosphere, like no atmosphere, to protect the planet from solar radiation, from the hot or coldness of space. Like it was just a world of extremes. Okay, so needless to say, there was probably zero life, at this point. Now, as scientists go on in the Earth's history, they presume that after a while, the meteor impacts would subside. There would be fewer and fewer impacts, and so planets were just left with whatever internal heating they had to kind of keep them molten, and the outer crust would have been exposed to the vacuum and coldness of space. So instead of staying molten on the outside edge, the idea was that the Earth in its infancy probably developed some sort of thin layer of cold rock that formed as the magma started to, well, cool off and solidify from being exposed to the coldness of space. That cold outer layer, well, it was thrust upwards by the internal heating from the mantle and pressure that would form from that internal heating. And that thin crust got thrust upward, maybe tens of thousands of feet into the air and formed volcanoes. These volcanoes acted kind of like chimneys at a factory, right? So they would throw up smoke and ash into our quote unquote non existent atmosphere. And as they put smoke and ash up into the atmosphere, maybe tens of thousands of feet up into the sky, well, that blanketed the planet, kind of creating a solar shield that would continue cooling the planet because now, you didn't have the sun's rays penetrating all the way to the surface of the earth. So like this cloud layer laden with all kinds of chemistry, like blocked out the sun and continued the cooling process, right? So these volcanoes could have spewed some lava and that could have added to the surface, but more importantly, they spewed gas, relieving pressure on the inside of the planet and like starting to form our primitive atmosphere. Still no oxygen, and realistically, nothing could survive yet. Okay. Scientists think at about 4.4 billion years ago, well, the Earth might have cooled enough for water in the atmosphere to condense. So they say, well, maybe at 4.4 billion years ago, it started to rain. And boy, did it. It rained enough, according to scientists, to literally cover about 70% of the Earth's surface with water, right? Millions of years of rainstorms and lightning, right, to fill every depression in and around these volcanoes, and maybe even to like cover some of the volcanoes up with water, giving our planet its oceans, like at 4.4 billion years ago. So it's just a speculation. I don't know, beyond a shadow of a doubt how they came up with this number, but I think realistically they took something that kind of had the same kind of chemical composition as our planet, heated it up, and then they kind of measured how long it would take to cool down under conditions similar to the early Earth, and multiplied it out by the volume of our entire planet. Okay. Now, how could they prove it rained 4.4 billion years ago? Honestly, they can't, because there aren't any fossils of raindrops in rocks that are 4.4 billion years old. So it's kind of a ballpark guess. Anyways, so at 4.4 billion years ago, scientists think the oceans formed. Okay. And again, there's no direct evidence of these early years of Earth's history. The oldest rocks that have been found on Earth are actually 3.9 billion years old. So anything that happened prior to 3.9 billion years ago, it's scientists' best guess. Rocks, well, rocks cannot provide information about everything that happened in Earth's infancy, but they are important, an important source of information about like life that came later on, as things, like came out, became visible, evolved, if you will, showed up on our planet and maybe went extinct. A lot of those things like fossilized and kind of gave us a little snapshot of what we, had creeping and crawling around this planet, years ago, decades, millennia ago. So fossils are our best clue about the past. Realistically, Mr. Kennedy remembers it like it was yesterday. I got my little journal and I recorded everything that was going on, but I'm keeping that to myself because, I want scientists to have something to discover and, to be excited about. So yeah, about 95% of the species that have existed on this planet are thought to, have gone extinct or be gone forever. They are no longer here. Of that 95% that have gone extinct, only a small fraction would actually fossilize, because, in the way I describe it is you have to die just right to become a fossil. So, small fraction of those 95% probably died just right to become a fossil. And then even if you died just right to become a fossil, well, somebody's got to find you. So there could be fossils in the ground that, might explain lots of things that happened in the past, and we just haven't found them yet. So we use fossils to learn about ancient species, right? A fossil, simply put, is evidence of an organism that lived long ago, preserved in Earth's rocks. Here's a few different types of fossils that, we look for when we go traipsing around, digging through rock strata, looking for clues to the past. We might look for trace fossils, casts, molds, petrified or mineralized fossils, or amber preserved frozen fossils. And there's just a little description about each of those. Okay. The scientists that study these fossils are called paleontologists. If you've seen the movie Jurassic Park, right? So those guys that studied the dinosaurs, like those are paleontologists. They're like detectives who use fossils to try to paint a picture of what happened a long time ago. And realistically, right, because of the fact that not everything fossilizes, and even the stuff that is fossilized that, we haven't found it all, there are big gaps in our knowledge of what has happened in the past. So, a lot of what we read in the fossil record is realistically science's best guess at kind of how things happened. And we're working all the time to try to fill in these gaps, but, the record's not complete yet. Paleontologists also study fossils to gain knowledge about ancient climate, not just who or what was alive, like when was the T-Rex alive versus like, I don't know, a brontosaurus or something, but also, like, was the planet warm? Was the planet cold? And they do that by studying the condition, position, location of rocks, along with like maybe the plants that are in them. So if you find rock strata that has like nothing but ferns in it, you have to assume that at that point in the Earth's history that that layer of rock was laid down, it was probably quite tropical and warm because ferns don't like snow, right? So there you go, right? That's what they're doing when they try to explain the Earth's history. So the only other question mark you might have, because most people would agree that ferns don't like snow, is like, dude, like how long ago was that? And how long did this warm period last? And like, why did the ferns die off? Right? Did it suddenly get cold, or I don't know, was there something else that killed them off? So, studying the condition, position, and location of these rocks is really, again, paleontologists not only trying to tell you like what animals were around, what plants were around, but even like what were the conditions of the planet? Was it a tropical planet, for a million years, and then it turned into an ice cube, or what? Right? The best fossils have been found, and the best place to look for fossils in rock that is laid down in layers. We call that rock sedimentary rock. For fossils to form, organisms usually have to be buried in mud, sand, or clay very soon after they die. And notice it says organisms. So like anything that we find in fossils, whether it's plants or animals, like they have to be buried really, really quickly soon after they die to prevent them from decomposing. If they decompose, then like, yeah, you're out of luck. It won't fossilize. So most fossils are found in sedimentary rock that is formed at relatively low temperature and pressure, and as a result, does a really good job to preserve these organisms. Fossils are not usually found in other rock types. Any rock that is formed under high pressure, high temperature, or some combination of the two, forget about it. Like that destroys the fossils, okay? Another good place to look for fossils is ice, right? So glaciers and things like that. It's just that that's not real fun to go dig around in. Makes sense, right? Um, Few organisms become fossilized because without this burial, like I said, bacteria and fungus like decompose their dead bodies. Sometimes even like scavengers will just like rip them apart, and then it's like, what do you have left, right? Occasionally, organisms do become fossilized, and it does take many, many years for that to happen. And even if they did become fossilized, like that's fantastic, but somebody's still got to find the thing in order to like learn about the past. This picture is just sort of meant to illustrate the entire process of fossilization by looking at my, highly intelligent buddy, the Protoceratops there that's drinking at the edge of this stream. So in order for you to become a fossil, you got to do something silly like this Protoceratops goes over to get a drink, and then whoops, as you see at step 2 there, it falls in the water. And as it falls in the water, apparently it can't swim or like make it to the other side. And the stream like covers the body with mud, sand, silt, or clay, and prevents decomposition. So over time, this thing starts to mineralize at the bottom of this stream. So that's fantastic. It can start to fossilize at that point, but it could take centuries for that fossilization process to be complete. Maybe the stream meanders on or dries up as that occurs, and we've got bones that are trapped now down in rock strata. Now here's the crazy part about fossils. Like there's not like this little red flag at the surface that says, hey, dig here, there's a dinosaur down here, right? So honestly, it's a lot of blind dumb luck that like paleontologists can discover these things. Maybe erosion occurs from like a glacier or a landslide, or maybe there's an earthquake in that last picture there that exposes a piece of the fossil, and then people go, ooh, I'm going to dig there because that looks pretty neat, and they discover the fossil. Okay, so at the end of the day, right, there could be fossils all around us underground. We just can't find them all. Okay. Now, the next thing we got to deal with in this particular chapter is how do we figure out how old something is? So I asked you, in class to do a little activity on relative dating and radiometric dating. So I'm going to go through those two processes with you here just to make sure we get it. Okay. Relative dating is not what it sounds like. It's not dating a relative. Relative dating is trying to determine how old something is based on, its relative position in rock strata. Okay. So if you think about this picture here, the idea is that, hey, if you can determine it takes like 1 million years to lay down a layer of rock, and then these layers are undisturbed, the stuff that's at the bottom of this stacked layer of rock have to be somewhere around 4 million years old because it takes 1 million years to lay down rock, right? So that's how, you know, this relative dating thing works. Everything that's at the surface is young, and as you go layer after layer after layer, things get older and older and older, assuming, right, that these layers are undisturbed. Like, it kind of makes sense because you can't lay down a bottom layer, but after you've already laid down a top layer, like there's no way to like sneak it underneath. Okay. So scientists use this to try to figure out how old something is. They got to figure out like how long it takes to make a layer of rock in order to have any hope of having anything accurate. Now, if you look at this picture really closely, there's a couple of other things that scientists do with fossils in relative dating. If you look closely, you should be able to determine or at least guess what the Earth was like in each of these layers. Like in a layer like this one here, you can see sea creatures. So maybe the area in question was an ocean at one point. But if you look someplace like this, these kind of look like big insects, maybe, forest. So maybe there was a forest here and then it flooded and became an ocean. And then all of a sudden you got these things that look like lizards that probably only live where it's hot and dry. So the ocean dried up and became a desert. That's something else that, paleontologists do. And then there's this. So they look at the fossil record and they go, I wonder where this lizard came from. So then they go back through the fossil record and they go, well, this lizard couldn't have just like magically appeared. So I'm betting that it evolved from something that looks kind of like it in the past. So I need to look at fossils from the past that maybe have ribs and a tail of some sort and a head. Ooh, here's a fish. Like, I wonder if the fish evolved into the lizard because, like, there's nothing else in the past that has ribs and a tail and a head that the lizard could have come from. So they try to make connections this way. Can they prove that the fish became the lizard? Absolutely not, right? It's a guess. It's a speculation. It's a human being looking for a connection or an explanation, just trying to connect two dots. But there's really no proof because we don't see fish becoming lizards today, right? So these are all things that you do with relative dating, okay? So in relative dating, the fossils in the top layer must also be younger than those in the deeper layer. And using that principle, scientists can determine the relative age and the order of appearance of species that are preserved in the fossils. That brings us to radiometric dating. All right, so in radiometric dating, we're not going to use rock layers this time. We're going to use like radioactive isotopes. So at this point, we're trying to find the specific ages of rocks. And we use a radioactive isotope in order to do this. Probably the most common one is carbon-14. Radioactive isotopes, well, these are elements from the periodic table that are unstable because they have an unusual number of neutrons. Neutrons are not something that's easily passed off by atoms. Unfortunately, it could take thousands of years for atoms to get rid of any extra neutrons because it's kind of like your ugly Christmas sweater that nobody wants, right? It's kind of like, look, I got this sweater, and people are like, no thanks. We've actually been able to mathematically model how long it would take for something like carbon-14 to radioactively decay to carbon-12, which is its ground state. And then what we do is we'll go and dig up a rock or a fossil and we measure how much carbon-14 is in the sample versus carbon-12 to kind of come up with an age. That's how it works. So it kind of works like, a chemical clock, if you will, because every radioactive isotope has a characteristic decay rate. This can set the stage for us to be able to say, okay, like this thing's 10,000 years old or 15,000 years old, and so on. So that's how it works, okay? We map this out or can graph this out in a chart like this. This is what's called a radioactive isotope's half-life. So scientists try to determine the approximate age of rocks by comparing the amount of radioactive isotope and the new isotope into which it decays. So if something is like 100% radioactive isotope, then it's probably pretty young. If it's 50-50 split, then it's reached at least one half-life. And at that point, scientists have to ask the question, like, okay, like how long does it take for carbon-14 to become carbon-12? So then this rock, it's reached one half-life, so the rock is about this old, right? If there's only a quarter of the radioactive isotope and then like 3/4 of the new, material, then it's two half-lives. And if you follow the graph, you get the idea. Okay, so scientists will use things like potassium argon, carbon-14, right? All these different things to figure out the age of rocks in this way. So in potassium argon dating, scientists know that potassium decays to its original form in 1.3 billion years old. So if they measure a sample, okay, and they find that potassium 40 is like all that's in the sample, like the radioactive form, then whatever rock you're holding in your hand is younger than 1.3 billion years old. If it's a 50-50 split, right, between the radioactive form of potassium and its ground state, then the sample is about 1.3 billion years old. That's how we apply half-life. Scientists know that carbon-14, right, takes about 5,700 years to reach a half-life. So same idea. If they measure a rock and they find it to be 100% carbon-14 radioactive, isotope, then basically the rock or the bone they're holding in their hand is younger than 5,730 years. If it's a 50-50 split between carbon-14 and carbon-12, well, then the sample is about 5,700 years old, right? If it's a 1/4 carbon-14 and 3/4 carbon-12, well, then the sample's about what? 12,000 years old. That's how it works, okay? So scientists always analyze lots of samples of rock using as many methods as possible so that they can obtain consistent values for a rock's age. But they also understand, that mistakes can be made. And, at the end of the day, that's why the word about is thrown in front of just about everything that they date. It's about this old or approximately this old, because they can't say beyond a shadow of a doubt, this is exactly how old something is. All right, ladies and gents, this is the end of part 1 of your chapter 17 notes, a little history of the earth. When we come back, I'm going to take you through geologic time and lay out from the origins of life through today for you in kind of a timeline. So that sounds exciting. I'll see you in a minute.